AC Servo Motor. This particular experiment. In that you will hear a term called incremental transfer function. We all know what is transfer function, right? It's the ratio of Laplace transform of output by Laplace transform of input at zero initial conditions for a linear time invariant system. Or else it is the impulse response of Laplace transform of impulse response of the system with zero initial conditions. Laplace transform of impulse signal is 1. That is how denominator. This is for linear time invariant system. But if the system is non-linear, we cannot find out this relationship. So for that, I am going to tell how we are going to linearize the system. So you can interrupt me if you have any doubts, okay? Y is equal to x, is it linear?
Yes, sir.
Y is equal to mx, is it linear?
Yes, sir.
But it is not a dynamic system, it is a static system. This can be V is equal to IR, voltage, function voltage is R into I. This is like current, I is equal to V by R. Current depends upon the applied voltage and resistance of the element. So this is a linear relationship, but this is a static system. It is not a dynamical system. There are no transients. Just if you apply input, you will get output immediately. Now, going ahead with this, y is equal to x square. Is it linear?
Yes,
No. If I ask you to linearize this, what will you do? What will you do?
we will make a tangent.
You will make a tangent. At each and every point, you will make a tangent. So when I ask you, you will say, you said that what you are doing is dy by dx is equal to 2x. But this is not the linear relationship. We will find dy by dx, say at x is equal to 1 is 2. So dy by dx is equal to 2. This implies dy is equal to 2 dx. And this is valid at x is equal to 1 only. So this is looking linearized. This is looking linearized. But what we have is dy is equal to 2 dx. But generally we drop the d's. Y is equal to 2x and we say this is the linear approximation at x is equal to 1. That is how it is being linearized around a particular point. That is why it is called, it is actually dy by dx. dy is equal to 2 dx. That is why this is called incremental relationships. This is valid only around that small neighborhood. But we generally drop those d's. The same extending it to, this is a static case once again. No differential, no derivative terms. Y dot plus y is equal to x square. Then we can arrive at this as you told from intuition, I have accepted. But how to arrive at this is, we will take y plus around that point, we will take as incremental change. You will take that neighborhood and x naught plus delta x whole square. Okay. X naught square, delta x is small, so delta x square is very small. X naught square plus 2 delta x naught. So this is once again y naught and x naught square, they get. That is how you are arriving at this. If you put the value of x naught, you are getting delta y is equal to 2 delta x. This is for a second, but if you go for third order, if it is nth order, then you will use Taylor series expansion. And you will only take first order terms and you will neglect the higher orders because square and subsequently all of they can be neglected. Around that, if delta x is small, then other things can be neglected. Same thing, if I apply it for this differential equation case, just I need to take that operating point. Okay. Fine. x naught plus delta x whole square. So it will turn out like y naught dot plus y and this x naught square, they get cancelled out. Because this, if you put x naught here, it is the same, and delta x to delta x, x naught, and it is plus delta y dot plus delta y is this one. So if I take Laplace transform, it is del s into delta ys plus delta ys to x naught is constant, this entire term is constant, delta x of s. So if I obtain that, if I consider x to be input and y to be output, then delta y by delta x is 2x naught by 1 plus s. So I am getting incremental transfer function in this case. Okay. So this is called incremental transfer function, and it is valid around that particular operating point. So we have understood this. When I ask a formula what is area of square, we call it a square. But they have derived it by some means, like some geometric interpretation and so on. But once they have derived, we are using the formula. Similarly, you have a state space matrix x dot is equal to x plus b, which you will be studying. So similarly, once you know this, there is a method called Jacobian Linearization. Like just like there will be, actually how it is derived is by using this Taylor series expansion. But they will arrive it with using means they will systematically represent. They will give the formula for finding linearizing a system around an operating point. But the basic principle is the same. Suppose if z is equal to function of x and y, this is single variable. Y is a function of single variable x. Z is a function of two variables x and y. So z is equal to x plus y, it is linear. Z is equal to mx plus ny, it is linear. But z is equal to x square plus y square, it is not linear. So for that you will use partial derivatives. You should have something like dou z by dou x at x naught comma y naught into delta x plus dou z by dou y at x naught comma y naught into delta y. That is how you will get delta z is equal to some constant multiplied by delta x plus some constant multiplied into delta y. Now I have many functions like that. Not z1, I have z1, z2, zn. Then I will get a matrix. The elements in that matrix will be numbers. How we will arrive at is this one. But that is valid only around a particular operating point. So AC servo motor, if I write the differential equation corresponding to the mechanical system, it is a rotating system, it's an electromechanical system. So it is J into that friction into d theta by dt. That's all. Because here no spring or such element is there. It is applied to, it is equal to torque developed minus load torque. Fine. The power rating of motor will be constant. Right? Any motor has a constant power rating. It cannot increase its capacity to do work. So its power rating is fixed. So, but when you apply load on the motor, what happens to the speed? It decreases. Power is nothing but product of speed into torque. For DC motor also, this equation holds good for any motor. Like electromechanical system, this holds good. For any mechanical system, this holds good, which is rotating. So power is nothing but product of speed and torque. So as power rating is fixed, it cannot deliver more power. It can deliver its maximum power, that's all. It cannot deliver its power beyond its rating. So if I apply low torque, what will happen is speed will reduce. But the product of torque and speed will remain constant. Okay. So what we are doing is we are actually interested in obtaining the torque speed characteristics of developed torque, but we cannot do that because what we can at max do is we can measure load torque and we can measure speed, but how this is happening is if speed decreases, torque developed is naturally increasing, but because of losses it will reflect at a lower level. So whatever we are doing for load torque, whatever we are drawing, whatever characteristics we are drawing, in a way they reflect the developed torque. Okay, so as I said,
So this torque is T developed.
The total torque, I guess.
yeah,
This is T load or T developed.
so that is what I am saying, like there will be at no load certain torque will be developed, but when you apply load, torque is still developed, but it will reduce because speed, it will increase, more torque will be developed, but speed will decrease, but power developed will be same.
So, which are
Fine. Do you have any doubts? This power is,
So I got it that this torque is torque developed.
this is torque developed means if
But
you
it
take
will
it,
decrease when speed will increase.
yeah. If you take it as T load, it is actually output. And if you take it as torque developed, it is power, mechanical power available. Mechanical power available. What I am saying is efficiency will not vary much. So whatever you are doing for load torque, if you are measuring load torque, then it holds good for developed torque also. Means that characteristic or that trend is that equally holds good for developed torque. So the speed torque characteristics of DC motor, they will be linear. This is speed and this is torque. Now we may get a doubt that torque is the cause and speed is the effect. So usually we should draw like this, but it is done only for constant power rating. It is not cause and effect relationship, but we are just seeing like how they are varying. So for AC servo, this is for DC motor. For AC servo motor, it will be non-linear. So torque is a function of, for AC servo motor, for DC motor it will be some constant multiplied into E and some other constant multiplied into theta dot. But for AC motor it will be function of speed and E. Okay?
So theta is
Theta is the angular position. Theta dot is angular velocity. Speed
okay. E
is the applied voltage. Here also same things. E is the applied voltage. So it will be a function of theta dot and E. So we have to linearize it. So this equation, if you put this here, it is as well as it is a linear equation. It's a non-linear. So we have to linearize it. That is why we obtain incremental transfer function for AC servo motor. DC motor, we will directly get the transfer function. So this completes your DC motor theory for DC motor experiment also. It is straightforward. So how I will do that is, if I have T, just from this analysis I am directly writing that linearized model. As I said, dou Z is something multiplied into delta X, something multiplied. So I am just writing delta T. What is that? Dou F by dou theta dot at that particular operating point. I am calling it, and it is multiplied with delta theta plus dou F by dou E at that particular operating point into delta E. I am calling this one constant. I am calling this another constant, say K3, K4. So if I obtain the speed torque characteristics from the experimental data, I can find out these things, right? Change in torque. Change in torque by change. If I have this graph, If I do it for different E values, this is for one E value, E1, E2, E3.
So this equation is for DC motor.
This is for AC. DC motor it is done. DC motor it is linear.
So then how are we getting these terms from this graph? This is for DC.
Sorry. Should have done it here. DC motor you don't like. Okay. I'm sorry. E1, E2, E3. Okay. So from the experiment we will find out this. If I substitute this, similarly I will get a differential equation. From here also I will get delta t, which is nothing but j into delta theta double dot plus f into delta theta dot is this particular same thing. So now if I apply Laplace transform on both sides, I will get s square plus s. I can obtain the transfer function. It is incremental transfer function. So this is how we are linearizing. Is it clear? Any doubts? So now we can try. Servo motor has two windings. That AC two-phase induction motor has two windings, reference and control winding. They're mechanically, those two windings are mechanically displaced by 90 degrees, and the power supplies applied to those windings are also have a phase difference of 90 degrees. When such a condition is met, a rotating magnetic field is produced or developed in the air gap. Rotating magnetic field means what? If you take this, at one instant, suppose the rotor is initially stationary. Let's consider this to be a rotor. And in the air gap, there is a rotating magnetic field. And if you fix one reference, there is a rate of change of, suppose if I fix this as a reference, this vector is rotating. So from here to here, there is rate of change of flux. This is a vector of some magnitude b, flux density. So there is a rate of change of flux. So EMF will be induced in the rotor, and the rotor is of that cup type of rotor. So there is a closed path for the current to flow. EMF is induced and there is a closed path for the current to flow. So once again now a current carrying conductor is placed in magnetic field. Because of this interaction of these two fields, a torque is developed and the rotor will rotate. This is the principle of AC servo motor. Now if you remember, I have been saying servo. What is the difference between servo and normal motor? Why don't I call fan as my servo motor? You might have heard like servo pumps.
Yes, sir.
But why don't I call servo fan? The specialty of that servo term is, yes, every motor is used to control theta dot, position or speed. But these are special purpose motors, like time constant, they should respond very fastly. Suppose this particular motor is used in an industry where it is used for cutting some metals or maintaining the thickness of sheets. If it does not happen, if there is a disturbance and if it does not go back to its normal value, there will be a drastic change in the quality of product. So similarly in war and defense applications, it should happen very quickly. These systems inherently respond fast. So time constant of the system should be small.
In
servo application. Suppose I can wait for even 30 seconds or 40 seconds or 1 minute for my fan to reach its full speed. I can wait. But if I wait for 40 seconds to track a target, then by the time I will miss that, there is a loss. So speed is very critical, means the fastness of the response is very critical. So that depends upon your moment of inertia. So in construction itself, they will maintain this length to diameter ratio such that smallest possible tau happens. For normal motors, it is because if you choose like this, there may be some other drawback or some other difficulty. But this particular care they will take. But normal motors, they will relax this condition. So this is the specialty of the term servo, AC servo motor. But servo basically means speed and position control. It's the variables, control variables are by default position and speed. Stop.